On behalf of 24HourAnswers.com, I welcome you to today's lesson. In this video, we're going to look at one example of the volume of a box that involves optimization. We will see several videos revolving around this same example, but we'll change some of the wording to make the problem a little bit different. A packaging company wants to create a rectangular box such that the sum of the length, width, and height will equal 64 inches. If the base of the box is square, what is the maximum volume that this box can have? So all boxes, rectangular prisms, have a length, a width, and a height. We want the sum of these three things to be equal to 64 inches. So take the length plus the width plus the height. We want that to be equal to 64. But let's bring in some variables. If the base of the box is square, so we're looking at this base down here, and it looks square, but don't worry about the picture per se. But if the base is square, that means the length and the width will be equal to the same measurement. I'm going to call the length and the width x. And we don't know what the height is, but we know we have an x by x base. The height I'm going to call y. Now let's bring back in the sum of the length plus the width plus the height needs to be equal to 64. So if we take the length plus the width, that's 2x, plus our height, which is y, this needs to be equal to 64. Here's one of our equations. We need to form another equation, and the next equation we're going to form is going to be the one we're going to differentiate, and that's going to be volume. And the reason why we're going to differentiate that is because we're trying to maximize the volume. The volume of a box is length times width times height. Therefore, if we take the length times the width, that's going to be x times x, that's x squared, times our height, which we've called y. Very similar to the earlier problems we've done with perimeters. Now what we have to do with this volume that we want to differentiate, let's get a variable by itself in this first equation. In this case, y is a good variable to get by itself. Moving the 2x over, we have 64 minus 2x, that's equal to y. Let's substitute that into this y variable, and then we can have a function, in this case, to differentiate, where we're just differentiating in terms of x. So now check out our volume formula. Length times width, that's x times x, times our height, which is y, but now we have y in terms of x, and that's exactly what I've plugged in right here. Let's distribute. So volume equals 64x squared minus 2x cubed, and now finally let's differentiate. V prime is equal to 64x squared. Its derivative is 128x. The derivative of 2x cubed, we have minus 6x squared. Now, notice what we have. We have a quadratic, really. Negative 6x squared. The power of 2 makes it a quadratic. Its leading coefficient is negative, guaranteed to have a maximum because this parabola opens downward, which implies you have a maximum. Let's set the derivative equal to 0, and now we can factor out an x from these two terms, leaving us with 128 minus 6x. So we have two factors here, the GCF, x equals 0. That's going to be useless here because obviously we don't have a box that's 0 by 0. We wouldn't even have a box. But taking this factor here, 128 minus 6x, and setting it equal to 0, we will find our value for x. Therefore, negative 6x is equal to negative 128. And dividing by negative 6, we have x equals 128 over 6. That simplifies to 64 over 3. And this is one of those long decimals. So I'm going to leave it like that. If you were to divide this, you would get somewhere around 21.333333 inches. But I'm going to leave it as 64 over 3 for right now. Back to our question. So what is the maximum volume of this box? Recall up here we have a formula for volume that's strictly in terms of x. Remember we had the x squared, that's the length times the width. And then we had our height, which was y, but we also got it in terms of x as well. Since we know what x is, we can plug that into here. But before I do that, I want you to notice something. If we take 64 over 3, which is the value of x, so that's our length and our width, if we plug that in, that x value into here to find our height y, notice what we get. We get 21.3 repeated. And I just mentioned that a moment ago. If we look at this fraction, it turns out our height is the same thing as our length and our width. The maximum volume we can get here, given that the sum of the length and the width and the height are 64 inches, but what's more important here is the base of the box is square. They're not telling us anything specific about the height. The maximum volume is going to be a cube. The cube is going to give you the maximum volume in this scenario. But I could easily change a few words in this word problem where maybe we don't have a cube. But we'll cover that in a future video. So answering this question here, the maximum volume, since technically x and y are both the same here as we saw in the calculator, we can just come here and cube this number because all three of our numbers are the same, length times width times height. Let's cube that, and our maximum volume is going to be this. Getting a decimal, the maximum volume is going to be 9,709, if we round off to the nearest whole number, cubic inches. And again, in example 2 and probably another example after that, maybe we'll have a square base, but maybe we want the height to be twice as long as the length or something like that. And again, we'll see that in future examples. And that's it for this video. I hope it helped. Be sure to check out our YouTube channel for more videos. Links to our social media are in the description below.